My name is Liu Ren, Director and Chief Scientist from Bosch Research and Technology Center at Silicon Valley. I'm responsible for our global research and advanced engineering on human-machine interaction, HMI at Bosch locations including Silicon Valley and Pittsburgh in the US, Renningen in Germany, and Shanghai in China. The focus of our global HMI research includes visual computing, audio analytics, natural language understanding, or in general conversational AI, smart variables and haptics, user experience and human factors, and much more. We develop intuitive, interactive, and intelligent HMI solutions to enable an inspiring user experience for Bosch products and services in application areas such as autonomous driving, car infotainment and driver assistance systems, Industry 4.0, and IoT, security systems, smart home and building solutions, healthcare, and robotics. In particular, visualization has been a key focus of visual computing research in HMI. For example, in scientific visualization, we have developed 3D ArtMap, the industry's first 3D navigation product that is powered by non-photorealistic rendering techniques on embedded platforms. More recently, we have been addressing key industrial challenges in areas such as Industry 4.0, IoT, and connected vehicles using visual analytics, an intuitive way of unlocking black box, data mining, or in general artificial intelligence solutions with data visualization interaction to enable explainable data analytics. Let's first take a look at the Industry 4.0 domain. Bosch is one of the main companies driving the Industry 4.0 evolution. At the center of Industry 4.0 evolution are smart factories. In smart factories, every status change or occurrence of abnormal events on the assembly lines is recorded and stored. The data collected can be used to monitor real-time assembly line performance and analyze historical data to identify when, where, and how assembly line production efficiency decreases, which is very good for troubleshooting and process optimization. We brought Industry 4.0 to IEEE vast community in 2016 when we received a Best Paper Honorable Mention Award for our work of using big data from manufacturing lines to support both historic data analysis and real-time monitoring. For example, the historic data analysis part visualizes manufacturing process as extended memory graph and supports interactive outlier detection. It allows factory workers to give examples on normal processes, which are used by the system to automatically learn the hidden rules and identify abnormal events. In this way, the users can incorporate their everyday experience in operating the assembly line for interactive outlier detection. We see that visual analytics also plays an important role for people to get insight from big data in IoT. Our work in IEEE InfoVis 2016 and IEEE VAS 2017 showcased good examples of using visual analytics to tackle challenges for predictive diagnostics, a key application in the domain of connected vehicles. As we know, modern vehicles record a variety of signals. This enables predictive diagnostics by effectively predicting errors or issues through observing fault patterns in a large number of vehicles. Repair shops can hence take actions preemptively, which could reduce warranty costs and increase customer satisfaction. We develop solutions that can trace the root causes of faults through interactive rule mining and extract the development pattern of these faults over time. Rule mining helps in finding if certain combination of signals repetitively lead to a certain fault. We use a space-filling layout to visualize all rules that predict selected faults in a condensed way. Vehicles that exhibited certain signals are visualized as a group. Large groups indicate signals that are repeatedly occur together. Color intensity indicate how likely a combination of signals will lead to a certain fault. For example, this rectangle reveals that when the events open circuit and lost antenna occur, the GPS becomes inoperative with a 72% probability. This is a step beyond traditional rule mining systems that rely on users to set appropriate thresholds and display the rules as textual lists. We can further trace the development paths of faults and give a comprehensive picture about how they occur over time. In our IEEE VAS 2017 work, we can do this by automatically detecting sequential fault development patterns and grouping the vehicles accordingly. Our solutions handles noisy data with fuzzy pattern matching and optimal pattern set identification algorithms based on the minimum description length principle to reduce visual clutter. The visual interface displays all the patterns and a list of faults in temporal order. The height shows how many vehicles match the pattern, and the triangles indicate the variations. We use locality-sensitive hashing to enable pattern detection at an interactive rate. We can observe a dominant pattern containing a lot of vehicles. We highlight this pattern and inspect the detailed information of the corresponding vehicles on the right panel. In this example, interestingly, we can see that all these vehicles with a specific pattern were sold in one country, indicating that the pattern is highly correlated to a geographical location. Besides Industry 4.0 and IoT, we're also looking at how to use visual analytics to address challenges in general AI. For example, more recently, there's increasing interest in experimental AI, which aims to allow humans to intuitively understand, better design, and appropriately trust AI systems. We see that visual analytics is one way to address the challenges towards experimental AI through intuitive and informative visualization and user interaction. A lot of work has been done to facilitate the understanding of the operation of deep neural networks. In our work presented in IEEE VAST 2017, we took one step further in using visual analytics to improve the performance and reduce the trial and error efforts through target model refinement when designing and training deep neural networks. Using image classification as example, based on the interactive exploration of confusion matrix, our system reveals that the network attempts to separate high-level groups in early layers and tackle fine levels in deep layers. Based on this finding, the user can leverage this hierarchical structure information to design loss functions that enforce the separation boundaries accordingly for fast convergency and higher accuracy. By applying these ideas to AlexNet, we were able to bring its performance to the level of GoogleNet, reducing the top 5 error by 30% on the ImageNet dataset and converging 3 times faster. In addition, we also developed a systematic way to quickly inspect training data quality and find issues such as ambiguities, mislabeling, and imbalanced distributions. Our current system can be generally applied to image classifiers. As a next step, we plan to develop further visual analytics solutions for different types of deep neural networks for other applications. As you can see, our visual analytics research focuses on key applications in industry. We always try to enable deployable product solutions with our innovations. We are located in Silicon Valley, a hub of HMI innovation in the world. And we are also working closely with academia, like PhD students, interns, and professors from universities in the United States, Asia, and Europe to push the boundary of visual analytics research.